Hey, this is Celso Batalha, Physics 4A, and I would like to go over the two exams. I'm not going to go step by step, but I will indicate solutions. So see how I go. So the problem number one is a projectile motion launched with an angle. Oops. Launched with an angle, and 40 seconds later it hits the same height as it was launched. So if you were to do some diagram, it would be something like this. You launch a projectile and the angle is given, and your projectile should go hit the same level at a time that is 40 seconds later. What is the initial speed of the projectile? So how do you do that? So we have an initial velocity given, and when you have an initial velocity with an angle is always a good practice. In fact, that's what you want to find. It's always a good practice to find its component. So in this case, the Vx component is given by V naught cosine of 60, and the y component is equal V naught sine of 60. And then you have, in this case, two components. You have x projection and y projection. So x projection is one that this velocity is constant, it doesn't change. And so the range or the displacement at any given time is given by your projected velocity in x, v0 naught, or v naught x versus time. And in this case, we know that v naught is v naught cosine of 60, v naught x is v naught cosine 60, and we have a time. So when we can't go too far here. We know the time, we could plug time here and find the range if we knew the initial velocity, but we don't have it. So the y projection is such that one interesting aspect here is that the initial position, y naught, is also equal to the final position, right? Whatever height that is, could be 0, but anyway, when you set your equation of motion, y minus y naught is equal v naught y, which is v naught sine of 60, versus time, the time is 40, minus half 9.8 times 40 seconds squared, right? So when you do that, this is 0. This is 0. And so which means allows you to cut some of your extra time, because the first time this projectile happened to be at that level is 0. So you can eliminate that solution, and then you find your V naught. You find your V naught as given by uh, 4.9 times 40 divided by sine of 60, something like that, right? So then you have your initial velocity. To find that's the magnitude of your initial velocity, and that is your speed. Now, what's the displacement vector 15 seconds later? So I don't know when 50 seconds later, 15 seconds later, but probably without a resistance, 20 seconds later would be half of this. So 15 somewhere here, but it doesn't matter. You could put anywhere. It really doesn't matter. So you want to find the displacement vector in this case. I think the other exam was to find the velocity. So the displacement vector is given by the x component summed as a vector to the y component, right? So what is your x component? Is going to be equal to this v naught, whatever number that is, cosine of 60 times 15. and your y component is going, which is the number here, right, is given by, you plug the same equation, right? So y, sorry, I need to use a eraser here. So your y minus y naught, so set it as 0, is equal to v naught, which we have, sine of 60 times 15 minus half of 9.8 is 4.9 times 15 square. And then you calculate how much that is, and then you have your y there. And your displacement would be the magnitude of it is the square root of x squared plus y squared. Okay, and pretty much that's it. What is your angle? Your angle phi is arc whose tangent is y over x, and then you are done there. Okay, good enough. That's for number one. For number one of the other exam, you want to find the velocity. So the velocity would do the same thing, except that let me see what is the initial speed. Yeah, so except that the x position for the other exam would be equal to whatever v naught it has cosine of the angle it had, right? I'm sorry, what I'm doing. So if you want to find the velocity in the case of the other exam, the vx is fixed, it's always the same, it doesn't change. Your vy can be calculated from your equation in v. V is equal v naught minus 9.8 times whatever time is requested. Okay, so that's the first one. Second, the engine of a locomotive exerts a constant force given. So we have a force given, 6.71025 newtons, and accelerate the train to some speed of 82 kilometers per hour. So we have to convert that to meters per second, just to make your life easier. Or probably not. Determine the time taken for the train of a mass given to reach the speed from rest. So which means, so this final speed is equal initial speed minus, oh, you want to find the time. Wait a second, that's not a good option. So if you want to find the time, final velocity is equal initial velocity plus a versus time, and we want to find this. So we have this, but we don't have that. So how do we find acceleration? Newton's second law, sum of forces is equal to ma, and then you have your force is equal to the mass times acceleration. So find your acceleration, plug it in there, and since you have this, you can get your acceleration. Okay. So blah 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 blah. Draw a free body diagram for the block of mass m. So the block of mass m is being pulled to the left by a force F. It does have its own weight, and it has the reaction of, it's a normal force of the 5 kilograms block on the block of mass m. So you have that one too. And it has also, since the force is pulling this to the right, there is no friction. Supposedly there is no friction here, right? Yeah, frictionless, so there is no friction here. So this force, let me see, the blocks are moving, so there is motion going on. So which means this force is able to overcome friction force, which means you have a tension force to the right, and you also have your kinetic friction. So you must specify kinetic friction to the right. Okay. So you have two blocks, mass M1, mass M2, hanging vertically, blah, 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 and you have acceleration. So the magnitude of acceleration is given in this problem. And both blocks move with the same magnitude of acceleration, although because they are connected by a cord that is not like an elastic, so the acceleration is the same, they move together. What is the coefficient of kinetic friction between the blocks of mass 1 in the table? I'm not going to do all the steps because we did this several times already in the lab. But basically, the coefficient of kinetic friction is equal to the coefficient we want to find times the normal force, and the coefficient we want to find multiplied by the normal force is the coefficient times mg, right? So we need to know what the kinetic friction basically is. So you do your free body diagram on block M1. There you have your M1G, and you have your normal force, which doesn't contribute to your motion in that direction, and you do have a tension force to the right, and you have a kinetic friction to the left. And aside of my free body diagram, I like to remind myself that this block is moving with an acceleration. When you do Newton's second law, sum of all forces in the x direction, and I'm calling my x direction, my x hat direction to the right as being the positive one, is equal mass times acceleration, and therefore T minus Fk is equal to m1a. Do the same with block M2, except that on block M2 you have two forces acting, weight and tension. Tension is the same, assuming the pulley is frictionless and massless, so that M2G minus T is equal M2A. Equation 2. So take these two equations and add them together. You eliminate T, and then you play around with your Fk, and then you find that Fk is equal M2G minus M1 plus M2 times acceleration. And then you can solve the problem because you find Fk, and then you can tackle that other part. Complete the free body diagram for the system indicator and ensure that the forces are named, blah, blah, blah. On the woman, you might need to be in this position to get it right. I'm not going to do that. So she is, obviously, she's standing on the floor. I would imagine this foot over here is keeping her balance. So she has a weight put in her core. She has a weight, her mass times g, that's the weight. And the normal force, you have two possible components. You have a normal force here, and you have a normal force there, assuming that she's touching. And I'm putting this vector kind of in a funny size. Shouldn't be like that, right? Because the normal force in this foot should be less than the other one. In fact, this should be bigger. Wait. Something like that. So, oh no, it can't be bigger than her weight, otherwise she would be jumping. Anyway, so I'm not picky on the vector size, but the direction is that, and you should be able to give different names to the two different normal forces. Now, the question is, she is keeping herself in position, and which means this foot might have some static friction that prevents her to slide to our right. And if this is the case, this foot also should be balanced out by a static friction, same magnitude, opposite direction. They should cancel out, right? So she wouldn't be moving, otherwise it would be kinetic. But you could argue that she is such a good athlete, and then you should write. She's such a good athlete that she's completely balancing herself on this leg, and then she doesn't have that. She's just touching her foot on the floor without exerting any action on the floor to that side. Okay, so if you don't put the static friction, I would take it as correct, I think. Although if you want to be picky and certain about it, okay, I have teenagers trying to get in the house. Just a second. So to be complete, you should be able to include that static friction. On the ball, no movement involved. So there is no motion, there is only a ball. The free body diagram would be you have a ball and you have a foot. So if there is no motion, you could say there is just a force that is exactly directed towards the center of the ball, and that is a normal force, is a force of contact of foot on ball. You do have, if you look at the ball over here, you do have the normal reaction, and again, I'm not obeying size of vectors, right? You have, I'm just writing to be convenient here. You have a normal force that is a reaction of the floor on the ball. This is a force of contact. But look at this. If she is directing the foot that way, see that? So we have a force that is moving to our right, which means this force has two projections. So if you do this force, let me expand it here. So you have two projections, right? I mean, two components. You have a vertical component, which is the one that balances with this, and you have a horizontal component. So you have to come up with a horizontal component as well. So that could be either, now you have to be clever. You have to say, well, you know, there is something that holds the ball in place, which I don't think is the case. So this normal force can be breaking down in two components. Now I'm thinking here. What I'm trying to say is this. So we have the ball. This is the normal force. So the force her foot exerts on here, if you don't want to have motion involved, has to be in such a way that you call this force of foot on the ball. So, and these can be broken down in two components. One radial, like that, and the other one like that, which is which you call static, right? and this is the normal. That's better saying that way. So I prefer this than what I did previously here. So I have a, in fact, let me take this away. So yeah, don't look at this. Don't look at this. Okay, so this is it. So in fact, let me change color just to make it more visible. So we have a normal force. Oops, let's see. So we have a normal force, and you have a force of her foot on the ball. If there is no motion, this force can then be break down in two components. One is the normal, and the other one is a static friction that runs that way. Okay, so when you add these two forces, you have the reaction has to be vertical, and everything is perfectly balanced. That's the force on the ball. On the dumbbells, no motion involved. So if there are no motion involved, you take one on another, and you have to have the two forces balance weight. And this is a normal force hand on dumbbell. Same thing on the other one. Two, no movement involved. On the man, there is no motion to the right, so he's not strong enough to keep that car moving. Oh, there is motion to the right, so the car is moving. So forces on the man. So you have the guy, make the guy as a point. You have weight. In fact, I have to kind of you have two contact forces here. Wait a second. One foot, another foot, and his hand. I think that's better that way. So go to his core, putting red. Go to his core, have his weight, and normal force. You have normal force 1, normal force 2. Now, the force on the man is the car that exert a force on him. So we could break down that in a normal force 3, and that is the car on the man. And now it's hard to tell. I mean, it seems that his arm is nicely perpendicular to the car, in which case it wouldn't have any friction there. But I don't know. You could go either way, a static friction upward or downward. I don't know. It seems that it's nice and perpendicular. I would say no friction in here, right, in this part. So it's just the force, the normal force on number 3. And now he is trying to pull the car forward, right? And which means if there is motion to the right, I would say, okay, let's say if there is acceleration, he start moving the car. If he start moving the car, that's a static 1 and probably a less static 2 here. These two forces combined make his system to move forward with a given acceleration, basically, and so the car moves. If and if you sum these two forces here, right? So if you sum these two forces, the sum of these two forces, if there is acceleration, must be bigger than this reaction over here, so that the net along the x direction should be bigger, and then acceleration would be the case. But if you want to argue this man is moving with constant velocity, these two forces here sum up should match the force the car reacts on him, and then he moves with constant velocity. Number 4, the one moves with constant velocity. That's it. mg and normal force. That's it. There is no force here. No, because velocity is constant. If velocity is constant, the net in x, sum of forces in x, must be equal mass times acceleration, and acceleration is 0. Extra credit. Our hero Tarzan swings on a 12 meters long, oh, I forgot to put meters, excuse me, vine attached to the highest branch of a tree. As the vine swings through the vertical detention. So what happens? So here's Tarzan, and then he goes chow when he's in the vertical right there. The tension, so what are the forces on Tarzan? He have his weight, 980 Newton. You have a tension cord right there, tension force. The speed Tarzan has at the lowest point. Well, if this tension is given, those are the only two forces acting if you ignore direct forces. So the center of rotation is given, then the net T minus weight is equal your centripetal force in V squared over R. So then it's a matter of writing this number here, right? Mass of Tarzan is 980 divided by acceleration of gravity. Then you have mass times V squared, which you want to find times R. And then you find V. What is the acceleration? Oh, his acceleration? His acceleration is the centripetal acceleration. Right there. That's it. Done. Okay. And that's the exam.